Okay, before we get to our other big lesson of this unit, we are going to focus on equilibrium, which is an application of torque without any newer concepts. We do go to some older concepts, but we'll focus on this. So equilibrium we have studied before when we talk about forces. It's when there's no net change in an object's state of motion. And so when we did equilibrium in the forces unit, we focused on objects that weren't moving, and that meant the net force on them was zero. And so we're just going to expand that understanding a little bit to deal with objects that are extended. We talk about extended objects as objects that can rotate, and then objects are just things that can't rotate. So for extended objects that have the capability of rotating, if they are in static equilibrium, not only is there a net force of zero on them, but there's a net torque of zero. To go even further than that, no matter what axis of rotation I should choose, because the object's not rotating, it should have a net torque of zero. So that's kind of neat, and it should make sense that if an object's not rotating, then its net torque should be zero, no matter where I choose its axis of rotation. That might spell trouble for your brain when you're like, well, it has an obvious axis of rotation, so I can't choose anything else, but you can. So you can choose any point on an object you want. As long as it's in equilibrium, the net torque should be zero. The last one has to do with center of mass. We also have the idea of center of gravity. And for objects that are relatively small, and I'm talking, smaller than the Titanic, they have the same center of gravity as their center of mass. And so center of mass is where the force of gravity occurs on an object. And so I'll show you what that means with our example. Back to diving boards for our example. And so we have a person sitting on a diving board. It's a very strangely designed diving board. Let me hopefully focus that. That's pretty good. And so this is the diving board, the part that's not filled in. There's a person on the end. There's a fulcrum. And then there's this enormous bolt that is holding it in place. And so you can kind of orient yourself if you think well, if that bolt wasn't there, then the person would just collapse the diving board and they'd fall right into the water. But because of that bolt is preventing the diving board from rotating clockwise and sending that person into the water. So, there's no question associated with this problem. It's just an exercise in understanding how to work with the net force of zero and the net torque of zero. So the first step is to draw a free body diagram. Because we're dealing with forces, we want to know what the forces are. The only difference here is we have an object that is extended, meaning there are a bunch of forces and they're all acting in different locations. And so I'm going to make this object a straight line. You can make your extended objects lines or circles or whatever shapes they are, and that's okay. So let's catalog all the forces. Now the person is standing on the board, and so the person is pushing down, and we're going to pretend that they're right at the end. The person is pushing down on the board with a force equal to their weight. So I will have that be mg, and that is the person. The diving board itself has its own weight. Now it might be small, but it could be very large also. This is an extended object, and so the mg for the diving board is going to occur at the object's center of mass. And so what you would be told in this problem is that the diving board is uniform in composition. And so if I go to the approximate center of the diving board, there is also the weight of the diving board. So that's the board. That is part of the net force on it, just like the net force on any object includes its own weight. So there's actually two forces of gravity that are acting on this diving board. Okay, now there's the fulcrum. Now the fulcrum is underneath the diving board, so the only thing that the fulcrum is capable of doing is pushing upward. And you can call this whatever you want. We'll call it F fulcrum, because why not? And so that's one of the forces. Now that should be pointing straight up, and that's not in my picture, but that's okay. And then the final one is the bolt. Now you have to apply some logic, which we just did. If the bolt wasn't there, then there'd be nothing keeping this end of the diving board from going up into the air. So the bolt has to push down. And so we'll call that F bolt. So there are 4 forces acting on the diving board: the bolt, the fulcrum, the diving board's weight itself, and then the weight of the person standing at the end. And so we are left to understand that the net force on all of this is 0, and the net torque on it is 0. Now, solving equilibrium problems in AP Physics 1 is very frequently solving a system of equations, and so that's probably going to be the case for the problems I give you, but I want to show you how to set things up. So both of these things have to be true. The net force one is relatively simple to carry out because it's the same thing it's always been. So all of these forces are either up or down, and so I can say that the force applied by the fulcrum minus all the other forces, the force of the bolt, big mg, little mg, is equal to 0. And I can do whatever algebra I want with that, but that is the only equation I need. Now, if there are forces in multiple directions, you can do net force in the x direction, net force in the y direction, and they're both equal to 0, but that's it. The net torque is also equal to 0, but I have to make a choice. I have to choose where on this picture I'm going to make there be a net torque of 0. So I'm going to label a couple pieces. I'm going to label this point A, B, C, and D. Now, the instruction is whenever you choose an axis of rotation, make sure that there's a force there, because that does something very nice for your equations. So I'm going to say the net torque is equal to 0 at point A. So there we go. All right. And so now I can make the net torque equation. Now, we've never dealt with net torque on a video, so I'm going to teach you how to do it here, even if I've already done it in class. You want to understand which of the torques could cause counterclockwise motion and which of them could cause clockwise motion. And it depends on where your axis is. So if I choose point A, I make the following conclusions. The bolt is not capable of applying a torque because the bolt's force is at point A. That means that the R for that torque is 0. And so by putting the axis at point A, in this thing I'm thinking about, the bolt is not capable of applying a torque. Okay, so that's fine. Point B is where the fulcrum is. Now the fulcrum's force is pointing upward. That would cause counterclockwise motion. So the fulcrum applies a positive torque. Both of these mg's point down, and they're to the right of the axis of rotation, so they would both be able to cause clockwise torque. So they're both going to be negative. So I can write the following equation. So I'm going to use these letters. I hope it doesn't get super confusing. But the R from A to B times the force of the fulcrum is the torque due to the fulcrum. Now, all of these forces are up and down, so I'm ignoring the sign of theta because it's going to be 90 degrees each time. So that distance times that force, and it's at a 90-degree angle, so that's fine. The first negative torque is mg, so that's the R value from A to C times mg, and that's the torque due to the diving board itself. And then R from A to D, and that's going to be times the force of the person. And all of this is equal to 0. So that's just like, that's one torque equation that I could do. And so if this works for you, you can use this. If the problem is to find the force of the fulcrum, maybe you can do that with this. If it's to find the force of the bolt, maybe you can do that with this also, but you've got to kind of figure that out for yourself. Just to give you one other example, I can also say the net torque is equal to 0 at, and I'm going to choose something for like maximum difficulty, at point C, using the center of the diving board as the axis of rotation. And so again, I can go through and like find my positive and negative torques. It's a little bit harder. So if point C is my axis of rotation, big mg has no torque associated with it because it's right at that axis. Little mg can apply a torque, and now here's the axis of rotation. Mg is pointed down and it's to the right. So if mg were the only force acting, the diving board would do that. That's counterclockwise. So mg is negative as far as torque goes. The fulcrum is to the left of the axis I've just defined and points up, which means if the fulcrum were the only thing that could apply a force, then the rotation would be clockwise for that. That's important. These two forces exert the same type of torque around point C. They both cause that clockwise rotation, so the fulcrum and mg actually have the same sign of torque in this situation. The bolt, on the other hand, is to the left of the axis that I've chosen and points down. And so this, if that were the only force acting, the rotation would be counterclockwise. So in this problem, the bolt is the only positive torque. So I can write the following equation. The distance between C and A times the force of the bolt. And that's going to be the torque due to the bolt. Now, all the other torques identified are negative. So for the fulcrum, the distance from C to B times the force of the fulcrum is negative. And then for the weight of the person, R from C to D times mg, and all that equals 0. So you get different torque equations depending on what axes you choose, and so you have to be clever about what axis of rotation you choose. That axis, I will tell you very bluntly, should eliminate as many unknowns as possible that are not important to your analysis. So, mg is something that's generally known, and so eliminating either the fulcrum or the bolt's force can make these problems solvable. Now, net force is going to have all of them in there, so what happens very commonly is you would use a net torque equation, maybe to find the force of the bolt. Like maybe you'd use this equation. You'd find the force of the fulcrum if you knew the weight of these objects. You could then plug that force into this equation and get the force of the bolt. And so it's very often solving systems of equations for this.